Hi, in this video I'll cover the basic aspects of ports in the Momentum EM simulator, and here's the agenda. So we'll go through some general concepts first, and then go into more detail about the parasitic effects. They're generated by ports, and look at what feed types are available in Momentum. We're going to look at specifically the situation with ADS 2025, and then talk about the Momentum port calibration options, and with an example, with a live demo of just jumping a bit ahead, how this new closed loop calibration works, and just look at its performance versus TML calibration. So let's get started with some basic terminology. So we talk about ports generally, but really it's important to distinguish between ports and feeds. So the port is the part of the structure that is essentially where we're going to be applying the excitation. And we define it by selecting or identifying in the structure one or more positive and negative terminals. And so this part, the port, is really the interface from the structure to the external world. And that allows us to then connect the signal that we're going to be using in circuit simulation to this specific part of the structure. Now, attached to the structure in EM simulation, there is the feed. Now, the feed is applying an excitation to the structure, and then based on this excitation, then the solution is going to be calculated and typically generate S parameters that then are going to be exported to circuit simulation for to get additional information on how this structure actually behaves from an electrical standpoint. So let's look at the momentum port. So the momentum port, again, is defined by selecting one or more pins for positive and negative terminals. So as we see here. Now the negative terminal can be defined implicitly, so explicitly, which is this case, where you actually get one specific point in the structure to be the negative terminal. But it can also be defined implicitly if we're using a cover layer in the substrate definition, or a reference pin on a specific layer or in a cover. And this is actually a case that is available in RF Pro. So as a brief aside, there's two different ways of using momentum in ADS. One is through EM setup, which is sort of the traditional way. But since a few years, we introduced a new interface to our EM simulators, which is called RF Pro, and that introduces significant improvements versus EM setup, and the ability to define what we call a reference pin on one of the layers is one of them. So it's one more option for doing an implicit definition of ports, of the negative terminals of ports. So one important point to keep in mind in a momentum port is that higher order and propagation modes are not calculated. So just fundamental mode, and that introduces constraints on the physical dimension of the ports, and you see them represented here from this picture taken from the product documentation. So you have constraints in terms of the port length, and also the edge width, and also area, essentially the dimension of the area here in case of area pins. And in all these cases, this dimension needs to be lower than lambda over 10 at the maximum frequency. If that constraint is not met, then warnings of this type are output in the simulation log, and I really encourage you to pay attention, and because every time these constraints are violated, then as you can read here, S parameters may become physical. In general, the extraction or the results you get from the EM simulation beyond a certain frequency, which is indicated here, are not reliable. So let's switch gears and talk a bit about the parasitics introduced by ports. So in momentum, the momentum ports introduces self-inductance type of parasitic effects, and that is due to the fact that when you connect an edge, which is represented by multiple cells here, to one point, um, there's these extra loops here that essentially create a self-inductance and an additional inductance called self-inductance. It can be represented as a series inductance between the point where we're going to be then connecting the circuit in circuit simulation and the actual structure. And this is an important effect that lower frequencies or with certain type of geometries is not going to have an impact, but in many cases it does have an impact, and that's also where we're going to be. That's one of the main reasons we're going to be using calibration techniques to get. Let's now look at this other effect, open-end capacitance. So what happens is when the structure is truncated here because we put a port, and in reality there would be, let's say this is a transmission line, or then if the port were there, then the structure would continue this way and we would now have this fringing field fringing effects here, which result into an additional capacitance, which is wouldn't be there if we didn't put a port. So that is an effect that is created by this disturbance of actually cutting the structure and to put a port in there. And so this is from a circuit standpoint, this can be thought of a parasitic shunt capacitance to ground, and this is this is the other main effect that is created there from a parasitic standpoint from adding a port to a structure that in reality wouldn't have a port. So we've covered this two main parasitic effects introduced by port. Well, let's look at how we can get rid of them. So typically the way this is done is by mating the port to what we call a calibrated feed, which consists of a source and a de-embedded fixture. So now this is, so the idea here is to be able to add this structure here, then independently characterize its effects, and then de-embedding these effects from the analysis here, in order to have just the effect of the that we will see, or the behavior of the structure that we'll see at the port without these parasitic effects. So let's take a look at what calibration or feed types we have available in RF Pro. So there are two places where we have access to this different feeds, of which each feed has, as we'll see, there's uncalibrated feed, which is direct, and then there's calibrated feed, which is the others you see in the list there, and they're available in the port setup here, so under the analysis. And this is where, by opening this port editor, you have access to the selection of the different options. So these are, with the ports can be defined anywhere in the structure, and typically rely on pins that are placed in layout or in virtual pins that are placed directly in RF Pro for physical location of this of the port terminals. Now, the automatic options you see here, which is the one activated by default, currently uses the direct, therefore, which is an uncalibrated feed in momentum. Another important point is with 2025 RF Pro, then we're introducing a new option here, which is called closed loop, which is essentially replacing SMD. So if you're using RF Pro or EM setup, well, the SMD calibration or feed type is not available anymore in RF Pro 2025. But we'll see more of this later. The other place you can find this feed type selection is in the component model editor. So as you see here, when you add components to your RF Pro extraction, well, if you open for each component, you have access to a window here that allows you to physically decide how you want to configure which pins you want to use for defining the component where the component is attached, and also a list of feed types, which is very similar to the one we just saw. So direct is there. Now as you may see here, TML is not available because it requires too much open space, and we'll see this shortly. But TML is not here. Fixture is only available for component ports, as it only applies to special cases involving component models. So again, I'll spend a bit more time on this later. And closed loop replaces SMD again from RF Pro 2025, as we just saw there. So now this is a bit complicated, but for those of you who are using EM setup and also earlier versions of RF Pro, try to just clarify a bit the chronology of how things happen. So for example, TML 0 length here is the nomenclature using EM setup. Now in RF Pro before 2025, we call it TML0, and now it's called open-ended. So the one you see in purple are the ones who have been consistent all along in nomenclature between RF Pro and EM setup. Now Fixture, as I mentioned before, is available in RF Pro, and starting in version 2019. SMD is in RF Pro before 2025 and is still available in EM setup, but in RF Pro 2025 is being replaced with closed loop, and also the open-ended now is what this TML0 length and TML0 calibration is now called, starting with RF Pro 2025. So let's review quickly the different feed types. So we have the direct feed type, which is really, it's the uncalibrated, it's the basic momentum port that we discussed earlier. There's no de-embedding structure, and the feed consists in an ideal lumped source voltage, lumped voltage source, which is directly connected to the port. So it's really the basic momentum port that we just saw at the beginning. Then one important point is for calibration to be used in simulation, the positive terminal of the port needs to be placed on a conductor edge. It's the situation that you see here. Now, if it's placed inside the conductor, calibration, as you see here, for example, calibration is going to be automatically deactivated. And so in that case, the direct uncalibrated feed will be used, and a warning will be issued in the simulation log, and this is what it's going to say, and it's to say that the port, certain port is not on the edge between a conductive and a non-conductive region. So again, I invite you to pay attention to the content of the log, because this information is important in order to understand what the simulator is doing in terms of how it's handling the ports. So let's go to TML calibration. So in this case, again, a positive terminal must be on edge conductor. It needs at least lambda over 2 space away from conductor edge. So it needs to have some open space in this direction here. Let's take this port to be able to place essentially a transmission line, which is going to allow this lumped source to essentially the electric field to develop, so that when it gets to this point, the effect of that, as we discussed before, the effect of the self-inductance effect that is due from going from a lumped source to a finite the transmission line of finite width, is essentially the E can be de-embedded out. So this is essentially what happened. What happens? This transmission line is calculated and then its effects are de-embedded from the results of the simulation, and so effectively removes the port self-inductance and capacitance to ground parasitic effects that we discussed earlier. Now, this is recommended for transmission lines, as it has very low level of residual parasitics. This is very high quality port, as close as it gets to ideal behavior. Next is open-ended calibration. So you've seen this picture just a few minutes ago. So this, how does it work? Well, they basically estimate based on how the structure is, the physical dimensions of the structures. We estimate the value of this the open-end capacitance, and then again the embedded from the results of the simulation. So then we go to delta gap. So in this case, there are two feed lines are connected to the. So you see here, this is where the port would be defined. By the way, it only supports two terminal components, and both these pins here need to be on the same layer. So it can only be a horizontal port. And so it consists of two feed lines. So you see here, there's two light orange transmission lines with a source in between, a direct feed actually applied in between. Then really what this feed is for is to add physical. Let's say that here you have you can have a component placed here, let's say resistance, for example, in the structure. So when you use this port, actually what it does, and then let's say that this resistance, you're going to use an ideal resistor in circuit simulation. So what happens is that if you don't have a physical resistor here, well, the effect of current going through this gap here is not going to be modeled, and neither is going to be modeled the coupling of the current going through this gap here with another component or other structure that might be in the vicinity of this structure here. So essentially what this does is it adds the effect, which is self-inductance and coupling, to this gap, which is actually physically not there. So you want to have a gap because you have your resistor, but if you open the structure there and then you're forced to put an ideal resistor in there, well, this effect will not be modeled. So this is what the delta gap calibration does for you. So let's get to the special case here of fixture calibration. So what it does is de-embeds the parasitic coupling of the fixture feeds from the EM model. So for example, this line couples with this line here, and what fixture does, it removes it. Okay, so why would you want to remove it? Well, let's say that your component here, your component model, so again in circuit simulation you're gonna get the EM structure that you have extracted, and then you're gonna connect, let's say, an S parameter model, an RLC parameter model, whatever, a model here in circuit simulation, and let's say that this coupling effect, so this model is being extracted using a fixture in measurement, and the effects of this coupling here in the fixture have not been removed by the not being de-embedded out when the model was created. So if you use a model built this way, which is usually the case when you use let's say not enough not sophisticated enough de-embedding or extraction procedures. Okay, there are some cases where this is the case. What you end up doing is double counting this coupling, because one counted once in the EM extraction, counted twice because it wasn't de-embedded from the measurement, and so you basically essentially double counting it. So in those cases, we introduce, to deal with these cases, we introduce this fixture calibration, which allows effectively to just count this effect once, and it will be the effect that's already built into the model. So we'll be able to basically eliminate this coupling from the EM model, which in normal situation you don't want to do. But if your model already has that coupling built in, then again it will be double counting it. Let's finally get to closed loop calibration. This is new calibration model option available in RPro 2025. You remove self-inductance and capacitance to ground parasitic effects, very similar to what TML does, but does in a different way. Pins must still be on the conductor edges, let's not forget that. But the difference is with TML is that it doesn't require open space in front of the conducting edge here, okay, which is very important because you want to have, the idea is to have similar performance of ports that are inside the circuit where there's not this free space. And it replaced SMD calibration, which is limited to 2-port components, which was the significant limitation there. And it's recommended for transmission lines where there is not enough open space to use TML, as I just said. Let's finish off by looking at an example of this closed loop port, and then how its performance compares with the kind of golden standard, which is the TML calibration. Okay, so I'll walk you through the simple example. So what I did here is it's very simple. I mean, I created this 50 ohm line. So this line has been essentially the geometry is what gives us close, very close to perfect matching here. And I've been using a substrate, you see here, an alumina 10 mil substrate here, and I've set it up in a way that it excludes conductive losses, so that we can actually see the effect of the parasitics, and it's not hidden partially, at least, by the resistive losses of the conductors here. So I have perfect conductor on this layer here where the microstrip is going to go, and also on the cover layer. So just 50 ohm, and I use TML calibration here and here. So I'm not going to show you this. I'm going to show you, later where that gets set, but you already covered in the introduction. So the starting point here, let me deactivate these others here. So basically actually I already run the simulation, so we can see that when I run the simulation on this port here, on port 1, I look at the return loss, I get something like this. So and by the way, I'm going up to 40 gigahertz here, which is where I then go higher, because this is where the warnings about port width and height start kicking in. So with this kind of substrate, it can go a bit over 40 gigahertz, but not much more. But in this situation, as you see here, we stay very close to the center of the Smith chart, and this is the dBs11. I say we're around minus 30 dBm. This is where we start from. So this is our kind of yardstick. What I'm going to be doing next is I'm going to try 3 different calibrations. So internal port options here available. So as you'll see here, so I'm breaking this line into 3 pieces of the same length. And the center one is always going to be the same, and it's going to be just 1/3 of the line with TML calibration at both ends. In all 3 cases, it's actually the same circuit here, or the same structure. And because I can use TML, because I'm gonna have free space around it here, and I'll show you in RF Pro later the setup. But well, in this case, I don't have free space in this structure here that you see. There's a gap here, and I cannot use TML. So I have 3 options here. I'll use direct, which is the uncalibrated port, which will give us the full impact of the inherent parasitics of the port, of the basic momentum port. Then I'm going to try TML0, which is basically it's a port we can use as internal port, but all it does is essentially de-embed the fringing parasitic effect, the open-end parasitic effect, but really, we're gonna get the full self-inductance effect, and then we'll look at the new addition to momentum, which is the closed loop calibration for these two ports here. All right, so let's see what we get. So this is our starting point again. So now what we're going to be doing is, let me deactivate this 2 here for now. So we'll go step by step. And let me just show the setup here. So this is my 50 ohm line. This is like the full length. In the ports here, I look at all properties here. And I see that the feed type is set to TML, as I said before. So can I run the extraction here, then generate sub-circuit, and then put it in circuit simulation? I can actually look at the results right here, which would be the same, kind of the same thing here. So if I were to get the Smith chart and just get 1, I get the same thing I'm showing in the data display here. But let's close this now. And so let's look at the other 2 pieces here. So I'm going to have the 2 pieces with the TML port here, TML port here. This is a direct. We're going to be using direct the feed. So again, all properties, and you see the 2 external one are TML, the 2 internal one are direct here. So this is 3 here, and this is 3 and 4 here. So run the simulation, then just create the sub-circuit, and then place it on the schematic here, and then for the last piece here, I'll be the center piece. I've set it up in all cases with TML. So this is TML. So again, going back to here, I'm gonna have TML direct, TML direct, TML here, and let's see what happens. So I run the simulation. Let's go here and add S33 here, Smith chart, and to the graph here, which is going to be S33dB, and this is the situation. So you just see here the up to about maybe 15 gigahertz. You kind of stay within the minus 30 dB. But then starting from, again, this is very dependent on the structure, but starting from about 15, to 17 gigahertz in this case, then you start getting significant mismatch here. And that is due to mostly self-inductance, but also to the there's some amount of contribution from the open-end capacitance. Well, let's look at what this open-end capacitance impact is. So let's activate this one. So in this case, I'm going to have TML, TML0, TML, TML, TML0, TML. So we'll see the impact of the TML0 calibration there, and I'm going to be, well, let's run the simulation here, and let's plot the results. In this case, will be S55 here and S55 here. So what we see here is that, there's some difference here, but the bulk of the problem here comes from the self-inductance, which really the TML0 doesn't do. Well, it attenuates early on, but then as you go up in frequency, then it just we kind of tend to reach again that there's a crossover here actually with the direct calibration. Okay, so the bottom line here is, as you go up in frequency, both as direct and TML0 only have limited ability to just, so basically the parasitics, the basic pore parasitics impact result accuracy. So let's finally include the closed loop, and so in this case again, TML closed loop, TML closed loop, TML. We'll run the simulation, and now let's go plot the result. S77 here, and S77 dbs77 here. So, well, here it's a bit crowded. You kind of see that the curve here, the magenta curve is really, it's pretty tight around the center. You see better here what happens. So as you see, there it tracks the TML pretty well, and then it continues to stay low up to the 40 gigahertz mark. So definitely better performance in terms of return loss or matching than the other two options available here. Okay. So this is the conclusion of the video and the example. So hope you found it interesting.